Chow-motives for inviting me. I guess some of you have already heard this talk because it's a joint project with Nikita Simonov, and he has given a talk in Banff, I think, related to that. But I would like to thank the organizers for giving me this opportunity, because my goal today is to show you that the proof of the main theorem is not really hard, and I actually plan to more or less give the whole proof of the main theorem, though I've heard some people find the proof that's written in the paper a little bit too long and not so clear. So yeah, so I plan to explain to you that nothing is hard in this theorem, and that you can really work with algebraic Morava K-theories. And here's a short plan for the talk. I'll remind quite briefly algebraic cobordism and free cohomology theories. And of course, I'll remind you about algebraic Morava K-theories and categories of pure motives defined for all oriented cohomology theories, and what can we do in these categories of pure motives, what we're interested in, and how are these categories of pure motives different for different cohomology theories. And after that, there will be this main result and its proof. And in the end, there will be a small, one application to torsion and Chow groups of some quadrics. Okay, so let's start. I already told the organizers that unfortunately I cannot see the chat during sharing the screen for some reason. And please stop anyone stop me if there's a question in the chat that they should answer. Okay, let's start with recalling algebraic cobordism and free theories. And we'll work over a field of characteristic 0 and all varieties that will appear most likely to be smooth and quasi-projective, and if not, probably it will be pointed out. So what's an oriented cohomology theory of algebraic varieties? Well, first of all, for every smooth quasi-projective variety X, it gives us a commutative ring, which is sometimes graded. That's why there is a star, but sometimes it's not. And we'll consider different cases as well. And why is it a cohomology theory? Well, because there are pullbacks for any morphism between such varieties. And pullbacks are morphisms of rings, and they preserve grading if there is grading. But what does it mean for a cohomology theory to be oriented? Oriented means that there are push forwards with respect to projective morphisms. So if we have a projective morphism, then there is a map of abelian groups which shifts the grading, if there is grading, by the codimension of this morphism. And all this data of all the rings and pullbacks and push forwards has to satisfy several axioms. I've written them down. Well, of course, it has to be the pullbacks and push forwards have to be functorial with respect to composition of morphisms. There is A1 homotopy invariance for cohomology theories, projection formula, projective bundle theorem, transversal base change. These are all the, well, I hope quite well-known properties of cohomology theories in algebraic geometry. But we most likely won't use them. The one that we will use in the sketch of the proof is the localization axiom, which tells us that if we have an open subvariety inside X, and let's assume that X is connected, then the restriction map, so the pullback along this open embedding, is surjective, and its kernel comes from cohomology groups of all smooth varieties that live over the complement. So, well, we have to deal with the fact that we don't want any non-smooth varieties appear inside our cohomology theories. So we have to be careful what to write here. And one way to do that is to consider sort of all, just all maps from smooth varieties, projective maps from smooth varieties to these perhaps non-smooth closed subvariety of X. Yes, and the localization axiom tells this short sequence is exact. And again, I hope that this is a well-known property for most of the audience for the well-known cohomology theories. And examples of such oriented cohomology theories are the Chow groups and K0. And what we're going to discuss now is the algebraic quadrics of Levine-Morel. And what we're going to discuss a little bit later is the Jens algebraic Morava K-theory. So for Chow groups, I guess, and for K-theory, all these properties are well known, including the localization axiom. And for algebraic cobordism, they are all results of the construction of Levine-Morel and of their theorem about its properties. So what are algebraic cobordism of Levine-Morel? Again, I'll just like to say a couple of words to point out that you can sort of, to an extent, work with them because they are defined really, really geometrically. So the generators of the case group of algebraic cobordism of a smooth variety T is additively generated by morphisms from a smooth variety to T, which are, these morphisms have to be projective and of codimension K. I forgot to write that down. So this is a sort of a class inside here, which can also be noted the push forward of the identity element in the ring of cobordism of X once we have defined the algebraic cobordism. Okay, so these are the generators. So you can see they're quite geometric, and there are also very geometric relations between these generators, which are sort of cobordance relations over the projective line. But the main feature why they're called double point relations that you should allow some slightly singular fibers in your family over P1. And you have to be, well, you have to write them down. It's possible, but we won't use it, so I haven't written down. But I wanted to point out that it's quite explicit and quite geometric. And I would also like to point out that the transversality axiom, the transversal base change, allows to compute pullbacks in some nice situations. So suppose we have a projective morphism from X to T, and let's say a smooth morphism from Y to T. So in this case, this transversal base change theorem, which doesn't work for all pullback squares, but only for nice ones like this, tells us that the push forward of an element from X to T and the pullback to Y is the same as pullback to the fiber square to Y times X over T, and the push forward to Y, right? And well, if we just look at the identity element, the push forward of the identity element of X here is this generator X to T from the algebraic cobordism group of T. And we would like to know what is its pullback to Y. And because we can go this way, we can first take the pullback of the identity, but the pullback is a map of rings, so it has to preserve the identity, and it sends the identity of X to the identity of the Y times X over T. And so we get that the pullback of this morphism is this morphism. So again, it's quite explicit, though it doesn't work in general for an arbitrary morphism F. But sometimes it does, and it shows you that it's, again, quite geometric, quite explicit. One more important thing about oriented cohomology theories is that they have Chern classes. The first Chern class of a line bundle OX of D, where D is a smooth divisor, can be just defined as a push forward of the identity of this again, of the unit element in the cohomology ring of T, its pushword to X, well, we can just take this as a definition, and then there are ways to extend the definition for all line bundles, and to you can extend the definition to high chain classes using the splitting principle and the Grothendieck deconstruction. That works perfectly well in this case, mostly because we have taken the projective bundle theorem as an axiom of our oriented cohomology theories. An important feature of chain classes, though, is that the first chain class of the tensor product of line bundles can be expressed in terms of the first chain class of both of these line bundles using this simple formula. And in this simple formula, here we have a formal power series into variables, which has coefficients in the ring of coefficients of our cohomology theory. And this power series does not depend on these line bundles, neither it depends on the variety X over which we are considering these line bundles, so it's fixed for the cohomology theory. And of course, this is well defined. The right hand side of this is well defined because chain classes are, you can prove that they are nilpotent, and when you plug them into a power series, it works well. So the thing that is written here, this FA, is not just any power series into variables, but because of the properties of the tensor product of line bundles, it is a formal group law. I have decided not to include the definition of a formal group law, thinking that you might have seen one. But here's a couple of examples of formal group laws for Chow groups. I guess everybody knows that the first chain class is additive, and so the formal power series that we get here is x plus y. And it's not hard to compute it for k0 and to see that it's not x plus y anymore, but there is an additional term here. So it's not yet an indefinite formal power series, but still it's already, you can see that it's not just x plus y. And if you wonder what, how does the formal group law of the algebraic cobordism look like, there is a formula here, which is again quite geometric, though it's only clear that it works over after you base change coefficients to q. But again, we won't use it, so let me just ignore. Okay, so formal group laws is a well-known algebraic structure which was studied by many people before algebraic cobordism and complex cobordism appeared. And you can easily check that formal group laws over a commutative ring R are in one-to-one correspondence with the morphisms of rings for a specific ring called the Lazar ring. So this is just an easy exercise in algebra. The interesting thing, though, is that this abstractly algebraically defined ring, the Lazar ring, turns out to be the ring of coefficients of the algebraic cobordism. So the algebraic cobordism, being oriented cohomology theory, has chain classes, and because it has chain classes, it has the formal group law, and because it has the formal group law, there is a canonical morphism from the Lazar ring to the ring of coefficients of algebraic cobordism. And the theorem of Levine-Morel tells this is an isomorphism. Also, algebraic cobordism is the universal oriented cohomology theory, though we might not use it. Right, so we see that we have a cohomology theory with the additive formal group law, which looks like that, x plus y, with the multiplicative formal group law, which is by definition this one, and with the universal one. And the natural question is whether you can find cohomology theories with other formal group laws. associated to them in this way. And in algebraic geometry, at least in this part of the oriented cohomology theories that we study here, the answer is very easy. If you take algebraic cobordism and change its coefficients, then you can obtain any formal group law. How do you do that? So what's the change of coefficients? You have to choose a commutative ring A and a map from the ring of coefficients of algebraic cobordism to this ring A to change the coefficients. But we know now that this is isomorphic to the Lazar ring, and therefore defining this map is the same as defining the map from the Lazar ring to A, and therefore it's the same as defining the formal group law over the ring A. Well, and you have to check then that after you perform this construction, you will still have an oriented cohomology theory satisfying all the axioms we have said. That's not hard, and you have to check that the formal group law that is associated to that is precisely this FA. Again, it's not hard, but well. Okay, so the Chow groups and K-theory are examples of free theories. So they can be obtained by algebraic cobordism by change of coefficients. But we would be interested in other cohomology theories obtained from algebraic cobordism using this construction. Great. Before I give you a definition of algebraic Morava K-theories, let me remind you one more fact about, one more definition, one more fact about formal group laws. So if we have, oh, sorry, I should have erased at some point. So here K is a field of characteristic P, which is greater than 0. So if we have a formal group law over a field of characteristic P, we can look at the following power series denoted P times X, where we plug in X into the formal group law sort of B times. So if we denote Fa of xy just x plus y over a, then if we write down x plus x plus x plus x, and so p times, we should denote this like that. And if you work in characteristic P, it turns out that when you have computed this power series, it always starts with x to the power p to the power n for some n. And well, it starts, so it means that here we have an invertible coefficient. And in this case, this number n, which appears here, is called the height of our formal group law. So it can take values, all finite values, but you can also allow, I guess, the infinite value to mean that this power series is just 0. And an interesting theorem of Lazar tells us that over an algebraically closed field or a separately closed field of characteristic P, two formal group laws are isomorphic if and only if they have the same height. Well, what does it mean for two formal group laws to be isomorphic? I guess it's a very natural definition that there is a power series gamma, which starts with an invertible coefficient b0 times t, and so on, so that if you take the, if you sum gamma x of gamma y with respect to f1 is the same as if you first sum x and y with respect to f2 and then apply gamma. Yes, and this theorem tells us that over an algebraically closed field of characteristic P, there exists for each n you can show that there exists a formal group law of the height n, and up to isomorphism, this is the whole classification. Here's an example how you can construct a formal group law of height n. there is a power series called the logarithm, but if you don't know what it means, you can just look at this expression here. And so if you look at this power series of the form written here, then it turns out that this power series is actually defined over Z with coefficients in this variable Vn. And if you take this formal group law modulo P and you send, say, Vn to 1, then you get a formal group law precisely of height n. But this is just an example. There are many other examples which are not isomorphic to this one over Z or over Fp. Okay, so finally we can define the Ernst-Morava K-theory, and that's not the definition of the Ernst-Morava K-theory, but of a graded Ernst-Morava K-theory. Because what you have to do is you have to choose a formal group law over this ring of coefficients. And well, I have suppressed the grading so far, but let's now recall that there is grading on the Lazar ring because, for example, it's a ring of coefficients of the algebraic cobordisms that is graded. And a morphism of, we assume that here we have a morphism of graded rings. That is the same as to say that the formal group law is graded in the natural sense. So we take a formal group law over this graded ring, sometimes called a graded field, because the degree of this variable is non-zero, and it's precisely 1 minus p to the power n. And if this formal group law modulo Vn sent to 1 has height precisely n, has height n as defined above, then the corresponding oriented cohomology theory, corresponding free theory, is called a graded Ernst-Morava K-theory with mod p coefficients. Of course, there are variants of the definition where you can look at p-local coefficients, for example, which we will use, I think, in application in the end. And you can look at non-graded version by setting just Vn to 1, or you can look at non-graded version over ZP. And I have already hinted to you in the definition, but let me make a precise remark that Ernst-Morava K-theory is not unique for particular prime p and number n as a cohomology theory, and even as a presheaf of rings, but there are some uniqueness statements that you can prove. And we'll use them later, but we'll formulate it first. What we will also need is to understand how the isomorphisms of formal groups law that we have appeared already here in the theorem of Lazar, how do they appear in the world of oriented cohomology theories? Well, this is a sort of theorem of Pine-Smirnov, though this is a proposition because this is just a part of their theorem, that there is sort of Fantoria construction from isomorphisms of formal group laws to maps between free cohomology theories. So we have an isomorphism gamma between F1 and F2. We can look at the corresponding to F1 and F2 free cohomology theories. And there is this phi gamma, which respects multiplication and pullbacks, but it does not respect in general push forwards. But there is a precise formula that tells you what happens with push forwards, which is called a Riemann-Roch formula. Okay, and this is an isomorphism of, so we can say that this is an isomorphism of presheaves of rings. And using the Lazar theorem, you see that if we look at two Ernst-Morava K-theories, then after base change to Fp var or any separately closed field, you get an isomorphism of presheaves of rings. Okay, now let's recall the pure motives, and then we'll be able to get all this together and formulate some statements. So if you have any oriented cohomology theory, you can associate to it the category of pure motives with respect to that. So how do you do that? So first you define the category of correspondences. Its objects are smooth projective varieties of your field K, and morphisms from one variety to another variety are defined as this abelian group. So if A is not graded, for example, if we look at K0, which is not graded, then here you just assume that it's the whole group, the only group you have. Okay, so these are the sets of morphisms. This is an abelian category, so these are abelian groups of morphisms. And you also have to define the composition, which I assume you have all seen at least once in your life, so I haven't written down. And after you add formally idempotency to this category and invert, it's called the Tate motive or the Lefschetz motive, you obtain this category of pure motives corresponding to A. And of course, there is a functor from smooth projective varieties to this category. Well, first there is a functor to correspondences, which sends X to X, because objects are the same. And if you have a morphism from X to Y, it sends it to the class of its graph. So the graph is, you can say that's a map from X to X times Y, which is identity on X and F on Y. And so these are all smooth projective varieties. So this is a projective morphism, and well, I mean, in general, it's always a projective morphism. So you take the push forward of the identity here, and this is the class of the graph inside X times Y, and precisely lives in the right codimension here. And the composition of correspondences actually is so defined so that it will be a functor in the composition of morphisms sent to the composition of correspondences. Two brief examples. The first examples were what is this Tate motive Z of 1. You can consider the motive of a projective line and see that the motive of a point splits from it because there is you can choose a point on it, and you can consider the projection from P1 to this point, and this defines you an idempotent in this object. And if you split off this direct summand from it, what's left is called the Tate motive, and this is what you have to invert to obtain this category of pure motives. Okay, but I think that won't be so much important for our discussion, the inversion of this object. Another example is that if you consider an arbitrary, well, if you consider a quadric, and you would like to look at its K0 motive, then it happens that it's very often a Tate motive. So it's very often a sum of this object, and also the powers of this object. And it happens if and only if the discriminant of this quadric, when defined, is trivial and the Clifford algebra of this quadric is split. So you can see that the K0 motive of a quadric somehow remembers these two cohomological invariants of the quadric. But note also that if we look at the Chow motive of Q, then it is Tate if and only if the quadric is hyperbolic. So somehow the Chow motive of a quadric Q remembers all the information about the arithmetic of the quadric. Right, so what can you do with different cohomology theories, different categories of motives? So of course, if you have a morphism of theories, so it preserves pullbacks, pushforwards, and the grading, Then there is a canonical functor from this categories of motives with respect to this oriented cohomology theory to that, PMA to PMB. And of course, there is canonical functor from the omega to Chow, which gives you functor on the category of motives. And what Vishik and Nikita prove is that it is a very nice functor. So it allows you to lift the decompositions from the Chow motives to omega motives uniquely. And we can say that it yields an isomorphism of the set of irreducible objects, which is the same thing. So if you have a decomposition of the Chow motive of X like that, then there is a decomposition of the omega motive. And again, this will have to be irreducible. Okay, so what does it allow you to do? It allows you to sort of push the motivic decomposition from Chow groups to any theory A, because you can lift it to omega and then push it forward to any oriented cohomology theory. So the motivic decompositions of how many irreducible direct summands there are in the motive of X is somehow most difficult for Chow groups, as we have already seen in the case of the quadric, and K0 decomposition of Q is simpler than Chow groups. This is a very general fact that the Chow motivic decomposition is the the strictest, I guess, or the weakest, depends on your point of view, I guess. But what we would like to say here is that for Morava K-theories, there is a similar phenomenon, and precisely it says that the motivic decompositions over nth Morava K-theory can be pushed to motivic decompositions in K of M Morava K-theories where M is less than N. Oh, again, sorry, it's not written here. M is less than N. And this is done via an intermediate category of pure motives corresponding to some free cohomology theory, but I don't want to discuss this proposition, so let me just state it as a fact. And also let me note that once you have Morava K-theories with coefficients without grading and with algebraically closed field of coefficients, then the motivic decompositions, they do not depend on your choice of Morava K-theory, which can be easily proved by Riemann-Roch theorem and the Panin-Smirnov construction. So in this way, the motivic decomposition of X with respect to Morava K-theory sits in between the motivic decomposition with respect to K0, I'll explain why, and of course Chow groups, because the Chow groups is the sort of the strongest or the weakest motivic decomposition that you have. And why is K0 appears here? Well, I have forgotten to tell you that the height of the multiplicative formal group law is precisely 1, and up to some change of coefficients, K0 is the first Morava K-theory. And therefore, nth Morava K-theory is somewhere in between the first Morava K-theory, which is K0, and Chow groups. And it's, well, at the moment, it's all over FP bar coefficients. And a corollary, which is proven in our paper with Nikita, but not using this picture and a slightly different method, is that if you have a smooth projective homogeneous variety such that the nth Morava motive of it is already Tate, so it's a sum of z of I for some I, then for all smaller Morava K-theories the same is true, and here you can take Morava K-theory to be graded and to have local coefficients instead of FP bar. That is nice. Okay, so this is the end of the review part, I think. Now let me come to the main theorem and its proof. Are there any questions about this sort of recollection on all the motives and cohomology theories? Okay, so I think I've written in the abstract, but I haven't written here, and I don't want to make it precise, but there appears to be a close connection between motivic decompositions with Morava K-theories and cohomological invariants. But I would like to speak only about quadrics. So for quadrics, the prime number that you have to choose and work with is just p equals 2. And then the theorem says that the nth Morava motive of a quadric is state if and only if the class of this quadratic form corresponding to the quadric lies in the n plus 2th power of the fundamental ideal in the Witt ring. That is, if it's an even dimensional quadric, and if it's odd dimensional quadric, then it has to be of such form. So what does this theorem tell us? I already said that the K0 motive of Q, so sort of the case n equals 1, tells us that this motive captures information only about the discriminant of the quadric and its Clifford algebra. And while these guys, the Morava K-theory, they, of course, as I said, live somewhere in between Chow-motives, which remember all the cohomological invariants of a quadric, and K0, and now they remember, sort of remember cohomological invariants up to degree n plus 1. And this is this, I think, interesting connection between Morava K-theory and cohomological invariants. Okay, so in the last 20 minutes, I would like to prove this theorem. And let's start with the following proposition, that if we take a Feisty quadric of dimension, well, the Feisty quadric corresponding to a symbol of length m, such that m is at least n plus 2, so that the class of this quadric lives inside this fundamental, this power of the fundamental ideal, then for any smooth quasi-projective variety, the sort of their pullback map from the Morava K-theory of the variety X to the Morava K-theory of the variety X base change to the field of functions of this quadric is surjective. So the statement that this map is surjective for any X. And you can wonder what is the general statement, or how in general to check such statements for an arbitrary variety instead of the quadric. And here is a nice lemma, which we have proved together with Evgeny Schindler, but it goes back to Bloch and Schindler, so I think it's kind of very, very classical, though they have not considered arbitrary oriented cohomology theories because there were none at that time. So suppose we have, say, an oriented cohomology theory that satisfies the localization axiom, which is the main part of the proof. For example, a free theory, any nth Morava K-theory or K0 or Chow-motives, then this map, the sort of pullback map for any variety X for the field of functions of a specific smooth projective variety Y is surjective if and only if we look at X equals Y, then there is here on Y base change to KY, there is a canonical rational point coming from the diagonal embedding of y to y times y. And if, so this point gives you some class in this group, and if this class can be lifted back here, so if it comes from A of y, then this map is always surjective. And maybe let me very briefly say what's the idea of the proof. The idea of the proof is that so what is, so in one direction it's obvious that if this is subjective, then this has to be subjective as well. But assume that this class of the rational point comes from A of y. Because of the localization axiom, it actually tells you that the diagonal of y, the class of the diagonal of y in A of y times y, can be represented as sum of some element which comes from the first guy using the pullback, and some element that has support on some closed subset in y that is not y, but a proper closed subset. And then this group acts on this group. So this is this action of correspondences on cohomology theories. And the diagonal, of course, acts as the identity. Now, if you now take an element here and act on it by the diagonal, nothing happens. But on the other hand, we have this decomposition of the diagonal. And you can check that if you act by this guy on any element here in x times y, then it will come from the pullback along the projection to x. And if you act by this element to any element x, then it will still have a support on D in this second sort of on y, yeah. And that's the end of the proof, because what we want to prove that this map is surjective, but this factors through the pullback to x times y and the pullback along sort of not the open embedding, but almost the open embedding here. And if you want to show that this map is surjective, you take an element here, lift it to an element here, then you represent it as a sum of two elements, where one comes from here and the other comes from there, and so the other one dies in this composition, and we're done. And so what we have to do now is to apply this lemma to this Pista quadric. So we want to look at the class of rational point in the Morava K-theory of a Pista quadric after base change to its field of coefficients. Well, but Pista quadrics have this nice property that as soon as they get a rational point, they're split. And of course, they're split over its functional field. So this here in Kn of Q, K of Q, the class of the diagonal rational point is just a class of any rational point. So basically, you have to find a class in Kn of Q that after base change to the field of coefficients K of Q, or actually any algebraically closed field, becomes a class of a point. And the claim is that it's very easy to write this class down. This is just a class of a subquadric of Q of dimension 2 to the power n minus 1. And let me explain why is that. Before I do, let me know that here we assume for simplicity that I've sent this variable Vn to 1, otherwise you have to write Vn minus 1 here in order for degrees to be equal. So we want to compute the class of a subquadric in the split quadric now over like an algebraic closed field. So it's a very geometric question and has a very simple answer how to do that. So first of all, because this quadric has sufficiently small dimensions, so it lives inside some projective spaces over inside this split quadric Q bar. So this linear subspaces of Q bar, the subspace generated by them, it maps injectively along the push forward to the ambient projective space. And therefore, if you want to compute the formula here, the formula of this class in terms of these classes, what you can do is actually compute the formula for Q prime in terms of the classes of linear subspaces, but now in the projective space. So the problem is even simpler. Okay, so how do we do that? Well, we can do it in the whole ambient space, but know that the inclusion of a quadric to the whole ambient projective space factors through the smaller projective space just of dimension 1 more, where the quadric sits as a divisor. And the class of a divisor, as I explained in the beginning, is just the first Chern class of the corresponding line bundle. And in this case, the line bundle is O of 2. And the first Chern class of the O of 2, which is the O of 1 tensor 2, is by definition of the formal group law, is summing twice the first Chern class of the O of 1. And the first Chern class of 1 is a class of the codimension 1 linear subspace in P2 to the power n. And by our choice of Morava K-theory, because the height is equal to n, when we look at this power series modulo 2, it starts with h to the power 2 to the power n, which is the class of a point on the projective space. And there has to be additional summands, but in this case they all vanish because they all have their codimensions too big. So yeah, so this proves the claim. So this guy is the class of a point in Morava K-theory. And of course, we have on the quadric, not on the split quadric, but over the base field, we have the class of a subquadric of such dimension. So this class is defined over the base field. And therefore, the class of the diagonal rational point or any rational point comes from the base field for these Pfister quadrics. And this allows us to apply this lemma and to get the claim of the proposition. Any questions about this part of the proof? Well, let me give you a small remark here that we have seen basically that on any quadric over a sufficiently big dimension, you can find a class of rational point in the Morava K-theory. In fact, for a quadric of sufficiently big dimension, you can find lots of projectors on Tate objects for the Morava motifs of the quadric, and this is done by Andrei Lavrenov in his PhD thesis, and you can find a recent preprint of his with Nikita Semyonov and Viktor Petrov, where you can find this result. And so it's a quite interesting result that tells you that for an arbitrary quadric, the Morava motif of quadric has lots of Tate summands, and what's left is a motif that's geometrically, of course, it's a Tate motif and has rank just 2 to the power n if the dimension is even, and 2 to the power n is -1 if the dimension is odd. So all the information, like all the arithmetic information that contained in here, is contained in this small, if you think that n is small, this small motif here. Okay, so back to the proof of the theorem. We want to show that if the quadric has its class in the n plus 2th power of fundamental ideal, then its Morava nth motif is Tate. So because this quadric lives here, you can find the field extension of the base field, which is obtained from succinctly extending your field extension to the fields of Pfister quadrics of well, corresponding to pure symbols in this ideal, in this power of the fundamental ideal, and you can kill this whole the class altogether. You can kill the whole this whole group actually by these field extensions. And so after you take this field extension, your quadric actually becomes split, and its motive is of course state. But along all these field extensions, this map from kn of q times q to the base field extension was surjective. And now you can just apply the Ross-Nilpontons principle, which is true in this case by Stefan Gide and Bishik. And because this is now a split quadric, and you can apply the Ross-Nilpontons principle, you can lift all the projectors here to here, and to see that the motive of the quadric is split over the base field. And this is the end of the proof in one direction. Well, in the other direction, slightly more complicated, I guess, but short. If you have the class of your quadratic form, the class of your quadric lives in a smaller power of the fundamental ideal, then by the result of Orlov, Bishik, and Vygotsky, you can basically reduce everything to the Pfister quadrics, because there is a field extension so that after this field extension, the class of this quadric Q becomes a class of an anisotropic M-Pfister form, where M is the same as it was. But now, after the space change, if our motive of Q were Tate over the base field, it would have stayed Tate after the field extension, of course. But now this motive is up to some Tate summons and Tate twists is the motive of Pfister form, M-Pfister form from this fundamental ideal, or from this power of the fundamental ideal. And what you can do now is just check that this is not Tate for n, so that n is plus 2 is bigger than m. Because Bishik and Igita actually have computed algebraic cobordism of these quadrics, and you can do that, use this computation to see that. Maybe there are slightly easier ways to do that, but everything boils down to the Rost computation of the Chow groups of these quadrics. Well, and this proves that this cannot happen if this is Tate, this also had to be Tate, but this is not a contradiction. And this is the end of the proof of the main theorem. And in the last 5 minutes, let me give you just one application of the main theorem and explain to you that it's not just a structural result about the motivic decomposition of quadrics with respect to Morava K-theories, can actually, and many results about such decompositions can actually be applied to the study of Chow groups of quadrics. And this is because there are tools to go from Morava K-theory, but now with the p coefficients, to Chow groups with the p coefficients. The first such tool is what I call Chang classes, though they're not Chang classes in the usual understanding, not in the understanding that I've presented in the beginning of this talk. But these are some operations from K of n to Chow groups, satisfying some axioms and so on. But what's important that they're surjective for quite a number of codimensions. So if you take n equals 1, where it should be k0, the classical Chang classes from k0 to Chow groups, and they're surjective integrally up to equals 2. But if you p-localize, it will be true using the well-known Riemann-Roch without denominators or something like that. It's quite easy to see that it will be true for e less or equal to p, which is same as written here for n equals 1. Okay, so, well, I have started saying that algebraic cobordism are quite geometric, and you can work with them, try to work with them geometrically. But after we have defined the Morava K-theory, all this geometricity, or not all, most of it has broken down. We don't have any more geometric relations. So you have seen that we can prove some quite interesting properties using the geometry, so to say, of using the geometry only. But here, so we have these operations, but we don't know how to compute them, unfortunately, except for very particular cases. So instead of computing them, what you can do that is you can sort of find chain classes from nth Morava K-theory to itself, again, similar to the case of K0, but with some additional properties. And define the gamma filtration again the same way as it is defined for K0. And now this gamma filtration has a nice property that the graded factor of it maps rejectably to, again, it should be p-local Chow groups, sorry about that, up to codimension p to the power n, in fact using the same maps. But now this is a map of abelian groups here, and if you estimate this one, you can estimate this one. Another quite nice property of this gamma filtration is that if nothing happens when you change your base field with the Morava K-theory of your variety, then nothing also happens with these graded factors with respect to the gamma filtration. So in our case, when we had a quadric, which was not split, but Morava K-theory behaves with respect to it so that it is as if it were split, then you can compute these graded pieces of the gamma filtration actually over the algebraic closure, where it's quite geometric question again, and it's possible to compute it. And so what we have done with Nikita, we have computed that, and it shows that for these quadrics, so it should be quadric in either here, or if it's odd dimensional, it's 1 plus this ideal. Then for such quadrics, there is no torsion in Chow groups up to dimension 2 to the power n minus 1, and the torsion in the next Chow group, it's can only be cyclic with one generator, and it's at most z modulo 2 if the dimension of the quadric is odd, and it can be, well, our estimates gives slightly bigger estimates for dimension q even, but these estimates, again, they are bounded above by a function of n. Well, and again, in most cases, depending on the dimension of q modulo something, I think modulo 2 to the power n minus 1, this again gives you z modulo 2, but sometimes the estimate is slightly bigger. But anyways, so this seemed to be new results about the torsion in Chow groups of quadrics. And well, that finishes my talk. Thank you very much for your attention, and thank you again. Thank you. I would like to thank the organizers for inviting me here.
Thank you very much. Thank you. Let's thank the speaker. Is there any question? Any question? Any question? So there's a...
May I?
Yes, sure.
I'm not an expert in these things, and so this may be off topic. But in the homotopy theoretic version of these K-theories, there's the nilpotence theorem that says something like that the endomorphism ring of an irreducible object has Krull dimension 1. Is there anything like that in the motivic story?
Thank you very much for this question, but at the moment, nothing along these lines is known, and there is no conjecture what this nilpotence statement should be, to my knowledge.
This was a very nice talk. I just wanted to comment to ask if people were aware of the work of George and Wang and Xu on the generic fiber, the special fiber of motivic homotopy theory. Is that, it seems to be a very important result.
I think I'm not really aware, but if
I'll send everyone, if I can, a link in the chat to a reference for that. I think it's in
thank
the,
you.
Yeah, that's what. Thank you. More questions?
So this, if I understood this last theorem correctly, you found some new torsion classes in the Chow ring of a quadric. Is there a way of saying what it is actually geometrically?
So unfortunately, that's not quite the case. We have not found torsion class. We only have found bounds on the torsion in Chow groups. So one perhaps should expect maybe that these groups should also have no torsion classes whenever the quadric is not a Pfister quadric of the right dimension. But we don't know it yet. So this is our only bounds, and again, they come from, so the generators of the cyclic groups, if they are non-zero, they come from Chern classes of Morava K-theory on very precise elements. And you can write down like an element in the Morava K-theory of a quadric and apply this operation and get a class in Chow groups. But the problem is that, as I sort of mentioned, that this is very ungeometric. So we don't know how to actually compute or so to geometrically define these operations. Because, well, to an extent, we don't know how to define Morava K-theory except for the definition I have given. So there are certain problems with the geometricity of this thing, of the Morava K-theory and of these operations, which does not allow you to really explain what elements you get in Chow groups, but only to compute the bounds so far.
So this statement that the torsion is a quotient of C mod 2, that should be interpreted as there is one particular class that may or may not be trivial.
Yeah, definitely, yeah.
And okay, thank you.
Thank you.
So more questions, comments? I just have one small question. So can you compute the Morava K-theory of spin groups?
Yes.
So, and the answer will be like...
So yes, we can compute it as an algebra over F2, over F2, yeah. But we don't know how to compute the Hopf algebra structure on it.
Okay.
And the answer would be, so it's the same algebra as without the co-multiplication as for Chow groups, until the point where the Morava K-theory stabilizes, and this point is written down in the preprint of Andrei Lavrenov, Viktor Petrov, and Nikita Simonov, which was recently, like I think last week, uploaded to the archive. So there is in that preprint so far, there it's written at which point the Morava K-theory of SO of the orthogonal group, and I think, well, it's not a long way for a spin there. And so what's left not written down yet is that before that point it's the same as in Chow groups.
Okay.
May I say that I think in the topological case, there's some interesting old work by Yagita about the KN homology. of spin groups. About the Pontryagin ring structure on the homology.
Okay.
It may be wrong.
Yes. Yeah, probably you're right there. But I think it's still not known. I mean, even there are some works of Higita, not so old ones, about algebraic cobordism of some algebraic groups, but we don't have even, I think, don't have correct conjecture of what algebraic cobordism of spin and so should be.
Okay, so more questions? If not, then let's speak again for a wonderful talk.